In this lecture, we are going to continue the integration by partial fractions. So again, if we have a proper rational function, well, by the way, if it's improper, which means the degree of numerator is higher or the same as the denominator, you do long division to make it a polynomial and a proper rational function, okay? So after we make our numerator has lower degree than the denominator, we factor the denominator completely, and if you allow the coefficients to be real numbers, then actually the denominator can be factored into only linear and quadratic factors, okay? And the previous lecture we were talking about the linear case. If ax plus b or whatever its highest power is appears in the denominator, we're going to do, all the way up to the highest power. Its first power, its second power, its third power, all the way to the highest power as denominators, and each of them you have like a number on the numerator because you are having a proper fraction. So the degree of the numerators of these simple fractions will be 1 lower than the degree of the denominator. That's our assumption. Could be low, lower than 1 more. For example, when you see quadratic, the coefficient of x's could be 0. But the assumption is they will be at most 1 degree lower than the how do I phrase it? If the degree of denominator is 2, then the degree of the numerator will be at most 1. Yeah, that's what I mean. But when the degree of denominator is 1, which is linear, of course, the numerator will be either, 1, will be 0 anyway, as degree. They will be constant. And the best scenario, it's a 0, but mostly, we assume it's a constant. But again, part 2, we did it from the last lecture. Now, if you are having a quadratic factor, ax squared plus bx plus c, same thing, it could be repeated with a power, but if you have a quadratic factor in the denominator, you assume the numerator has 1 degree lower, which means you don't have the x squared term, but you have an x term and a constant. Same thing, you go all from the first power of the factor, quadratic factor, okay, this is the first power, you go the first power, there we go. You go all the way to the highest power that it shows up in the denominator q. And for each of them, you pair it with a linear numerator, aix plus bi. Okay, so that's the case for quadratic factors. And finally, you do the same thing. You compare coefficients, you set up your equation, you clear denominators, you compare coefficients and solve for all these ai's and bi's. So pretty much the same as the last lecture, except now we are going to deal with quadratic factors. Pretty much the same fashion. Just remember when the numerator will grow accordingly. Okay, your denominator is bigger, is quadratic now, the numerator will be ax plus b. Yeah. Okay, our first example, we are going to write this partial fraction. We are going to write this into a partial fraction decomposition. Our denominator is actually degree x squared to the second power. So actually is degree 5. Okay, and numerator is degree 3. So we do have a proper rational expression, which means you don't need to do the long division. You go ahead and set up the partial fraction. So my rational expression will equal to, the factors I have is x by itself with an a plus x squared plus 1. This is degree 2. So it will be bx plus c. And it has a square, which means I'm going to repeat with its squared, then dx plus e. Okay, so for each factor, you go to its highest power. And linear factor on denominator, you go for constant 1. Well, one number to solve for. And when you have quadratic x squared plus 1, the numerator will be 2 terms, x term and constant. Then I clear denominator, which will be the x times, this is the denominator I'm going to multiply on both sides. So pretty much I cancel this, and I'm multiplying x squared plus 1 squared to the whole fraction, and I'm getting negative x third plus 2x squared minus x plus 1, which is the numerator, equals multiplying by the denominator. The first fraction becomes x gets cancelled, a x squared plus 1 squared, plus for the second fraction I'm cancelling 1 x squared plus 1, so I'm having the x and the other x squared plus 1. And then finally my dx plus e, I'm cancelling the square of x squared plus 1, I'm having an x left. Then I multiply these out. For the first, it's a perfect square, so ax to the 4th power plus 2ax squared plus a. You expand x squared plus 1, you get x fourth plus 2x squared plus 1, you multiply by a. And then this, I guess I should multiply it a little bit, I guess. Let me do it here. So I'm having bx squared plus cx, right? That's what this gives me. I multiply x first times x squared plus 1. So this will be bx to the 4th plus bx squared plus cx to the 3rd plus cx. And I'll copy it here, bx to the 4th plus bx squared plus cx to the 3rd plus cx. And finally, I have the last product. I just distribute the x, which will be dx squared plus ex. Now I combine like terms. I have x fourth for 2 term, a plus b, x to the 4th. X third, I only have 1. So plus cx to the 3rd. Then x squared, I'm having x squared and x squared. So I'm having 2a plus b, x squared. One more, plus d. Oops. Plus d, x squared. And then x term, I'm having c and e plus c plus e x. And finally, I'm having my constant left, plus a. Comparing the coefficient x to the 4th power, I don't have it. So let me do the grouping later. I don't know how long it will be. A plus b equals 0. And this x third, c equals negative 1. X squared, 2a plus b plus d equals the coefficient of x squared, which is 2. And then c plus e is the coefficient of x, which is negative 1. And finally, a is the constant equal to positive 1. Sorry, I meant positive 1. And then I group them. So we already know that a is 1 and c is negative 1, right? And, well, I need to find b. I use this because I already have a. A plus b equals 0, well, a is 1. So b equals negative 1. Then I guess I'm going to use c plus e equals negative 1, since I already know c is negative 1. So negative 1 plus e equals negative 1. That tells me e equals 0. I have my a I have my b, I have my c, I'm missing d. So I need to use the third equation, 2a plus b plus d equals 2. Well, a is 1, b is -1. I don't know d equals 2. So 2 minus 1 plus d equals 2. Well, 1 plus d equals 2. D equals 1. Then you put them together. The original fraction over x times x squared plus 1 squared equals, I'm having a 1 over x plus bx -1, x plus c -1 over x squared plus 1 plus dx 1x plus 0. So I'm not writing the 0. X squared plus 1 squared. That's how I write my initial fraction into this partial fraction decomposition. Next, of course, we are going to use the partial fraction decomposition to find its integral. So let me again give you the partial fractions. It's 1 over x plus -1, x minus 1 over x squared plus 1 plus x over x squared plus 1 squared. Then the whole thing dx. Let's talk about strategy. Well, your denominator is x squared plus 1, or its power. So pretty much you are going to separate the numerator into the x term and the constant. The x term will be combined with the dx. It will turn into the denominator x squared plus 1 or x squared plus whatever, okay? And so you have like sort of power rule or log. And for the constant, when you have 1 over a quadratic, you are going to use this fact. Pretty much 1 over a quadratic is tangent inverse. We talk about this, how you are supposed to substitute x by a tangent theta, right, to solve it. But you can remember this as a formula because it will be so important. Every quadratic denominator, pretty much with a constant, you are going to use it. Okay, so let me rewrite my integral. I have my x, 1 over x term, and then I have my -1x, x squared plus 1 term, and then I have my -1 over x squared plus 1 dx. Sorry, I missed the dx. And then I have the integral of x over x squared plus 1 squared dx. So pretty much I'm having 1 term, 2 term, 3 term, 4 term with their according denominators. Okay, and then let me move the negative signs. Well, I'm not going to move it. I'll just do this. Okay. All right. Now let's do them one by one. The integral of 1 over x dx. This is log x. We don't know whether x is positive or negative, so we take absolute value. Then my next term, the integral of x over x squared plus 1 dx. This is where I want my x squared plus 1 be my u. So I need 2x dx, and then I 1/2 it. This is 1/2 the integral of the x squared plus 1. Do you see that? This is the derivative of x squared plus 1 with a dx over x squared plus 1. And if you want to, u equals x squared plus 1, this will be 1/2 integral 1 over u du. And this is 1/2 log u absolute value. Well, u is x squared plus 1, which is positive anyway, so we just have 1/2 log x squared plus 1, well, plus c. The third term, I'm having the integral of 1 over x squared plus 1 dx. That's the formula. This equals tan inverse x. I don't even need the parentheses because I don't have a denominator, x over 1, right? Plus c. And finally, I'm having the last fraction. I do the same thing. Because it has an x on the numerator, I give it a 2, I make it 1/2. So this is 1/2 the integral of 1 over x, sorry, going ahead of myself, x squared plus 1 squared d x squared plus 1. Again, u is x squared plus 1, and you're having 1/2 u negative 2 du, which is 1/2 u negative 1, 1 over negative 1 plus c. And this is negative 1/2, sorry, negative 1/2. And then u is, what's my u? X squared plus 1 plus c. Now I put everything back together. This equals log x absolute value, because you don't know whether x is positive or not, minus, I had this minus sign here, so minus my second integral 1/2 log x squared plus 1, and then my third, again I have a minus equipped, so it's minusing inverse 10 of x, and finally it was positive, but my integral was negative, so it's still minusing 1 over 2 times x squared plus 1. Then indefinite integral, I need a plus c. Well, so pretty much you rewrite your same strategy. You rewrite your proper fraction into the partial fractions, and then you find the antiderivative of each of the fractions. And if you have a quadratic denominator and a two-term numerator, actually you deal with the two terms on the numerator one by one. Okay, now let's move on to the next question. This question I'm trying to illustrate, when you have a more complicated quadratic denominator than the x squared plus 1, what would you do? You complete the perfect square. So pretty much I need to get that x squared plus a situation. So I will, on the denominator, 4x squared plus 4x plus 1 is the perfect square. So I keep that, and then I leave the 4 outside. dx. And this gives me the integral of 4x minus 2 over 2x plus 1 squared plus 4 dx. And I will just go ahead and call this my u, because I need a u squared plus a situation, a squared situation, whichever. So I will let my u equals 2x plus 1. When you do substitution, after you decide what your u is, this is what you do, okay, guys? Unless you see the 2x plus 1 sitting together, you are doing backward. You solve x in terms of u. So here what we have is u minus 1. Well, 2x equals u minus 1. So x equals u minus 1 over 2. Because you are going to replace every x in terms of whatever in u. Also the dx. You don't do du, okay? You do dx in here. So x equals u minus 1 over 2, or u over 2 minus 1/2. dx will just be 1/2 du. Okay, you do it backward. Then my integral becomes, my 4x will be 4 times u over 2 minus 1/2 over, this is u, the parentheses, 2x plus 1, it's u squared plus 4, then the dx is 1/2 du. They cancel to be 2, and then the 2 cancels these 2. So I'm really having the integral of u minus wait, I'm sorry, I lost my -2 here. I lost this -2, so let me go back. -2. Okay, then I can cancel this with this, and no, I can't because I have the -2. What am I doing here? So let me just multiply out. This is the integral of 4 times u over 2, 2u minus 4 times a half, 2 minus another 2 over u squared plus 4 times 1/2 du. Okay, let me just work it out. 2u minus 4 u squared plus 4 times 1/2 du. Now I can cancel them. I have the integral of u minus 2 u squared plus 4 du. Same thing, I'm going to separate it into two terms. I'm having the u term, u squared plus 4 du, and then I have the constant term, 1 u squared plus 4 du. Okay, then the u term, again, you are going to give it a 2.5 so that you are having 1/2 the integral, oops, I lost du. I'll keep it on the numerator, du squared plus 4 u squared plus 4. So this is 1/2 log u squared plus 4. It's a positive number, so I don't really need the absolute value, plus c. And on the other hand, the integral of 1 over u squared plus 4 du. Notice I have no u here, no variable, so this is the tan inverse. And the formula is 1/2 tan inverse of u over 2. So pretty much is u over the square root of the other number, and also times its reciprocal as the coefficient, then plus c. Now, keep going back to my original integral. So it is 1/2 log, what's u? U is the 2x plus 1 squared plus 4. Notice that this is my original denominator. That's my first term, minus 2 times 1/2 tan inverse u is 2x plus 1 over 2 plus c. Then they cancel each other. Well, you don't have to write it back as the original denominator, but I think it's nice to show the connection, so I will 4x squared plus 4x plus 5, taking away tan inverse of 2x plus 1 over 2, then plus c. This is how you are going to deal with the quadratic denominators, where you don't just have the ax squared plus b case. Okay, when you have the x term, you need to complete the perfect square so that you get to the a perfect square plus constant situation, so that you can use the tan inverse formula for the constant numerator, and you can push the x into the, well, change the variable, then push the x in the dx, so that you can do the power rule for the x term on the numerator. Now you can try practice number 1 and 2. Last part, I want to say a little bit about rationalizing substitutions. Now we have seen how we can solve all the integrals of rational expressions, polynomial over polynomial. So if somehow you are able to change not only the integral, but also, when you change variable, there will be the du coming out, right? So if you are able to turn the integral into a rational expression, it will, you know how to solve it. Okay, so that's what we are talking about here. When the functions are not rational, but somehow you are able to change it into rational, do that. Because as soon as you get the rational, well, again, quotient of polynomials inside, you can just do what we did in these two lectures. So in particular, if you see a radical. A natural thinking would be, let me get rid of that radical by saying the radical itself is u. So pretty much, you have radicals are rational exponents, right? You have fractional exponents. You make the smallest part like u, then the original variable will become the powers. In that way, you get rid of all the radicals. So for example, my question 3, I'm having, so in question 3, I have this integral of 1 over radical x plus 4. So I am going to make my u to be the radical. Again, when you do substitution, you do the backward. U is radical x, that means x is u squared. Then you just replace every x by u squared. This is 1 over radical x is u squared plus 4, and dx will be 2u du times 2u du. And u cancels each other. I'm actually having the integral of 2u squared plus 4 du. Or let me pull out that 2. 1 over u squared plus a squared du. So that's 2 times a is 4, right? So it's 10 inverse of u over square root of 4, 2. And then that one have also go to the coefficient plus c. 2 and 1/2 cancels each other, and my u is actually square root of x over 2 plus c. That's it. So again, please observe that when I make my square root, like the smallest root, as my u, all the x's will become its power, which means you get a polynomial or a fraction of polynomials. Then you can do what we did. Yeah, that's pretty much is the lecture. Now you can finish practice number 3.